IOI 2020, the most prestigious competition in informatics, International Olympiad in Informatics. Fourth problem, or we can say first problem of second day. Biscuits. The problem is the following. Packing biscuits. Auntie Kong is organizing a competition with X participants and wants to give each participant a bag of biscuits. There are K different types of biscuits numbered from 0 to K minus 1. Each biscuit of type I between 0 and K minus 1 has a tastiness value of 2 to the I. Auntie Kong has AI, possibly 0 biscuits of type I in her pantry. Each of Auntie Kong's bags will contain 0 or more biscuits of each type. The total number of biscuits of type I in all the bags must not exceed AI. The sum of tastiness values of all biscuits in a bag is called the total tastiness of the bag. Help Auntie Kong find out how many different values of Y exist, such that it is possible to pack X bags of biscuits, each having total tastiness equal to Y. Implementation details. You should implement the following procedure in 64 and count tastiness and the following condition and variables: X, the number of bags of biscuits to pack; A, an array of length K for I between 0 and K minus 1. AI denotes the number of biscuits of type I in the pantry. The procedure should return the number of different values of Y such that Auntie can pack X bags of biscuits, each one having a total tastiness of Y. The procedure is called a total of Q times C constraints and subtasks sections for the allowed values of Q. Each of these calls should be treated as a separate scenario. Examples. So let's see the examples. The most important things in these problems to just check the output and understand the problem says exactly what. So here we have three threes. What three? The number of bags. 5, 2, 1. It says this means that Auntie wants to pack 3 bags, and there are 3 types of biscuits in the pantry. So we have 5 of 2 to the 0, 2 of 2 to the 1, and 1, 2 to the 2. So 5 biscuits of type 0, each having a tastiness value 1, 2 biscuits of type 1, each having a tastiness value 2, 1 biscuit of type 2 having a tastiness value 4. Now, the possible values, let's check. If we want to check, we know that we have, if I want to just show you, we have 5 1s, 2 2s, and 1 4. So 5 1s, 1, 2, 3, 4, 5, 2 2s, and 1 4. So, and we have 3 bags. If I want to reach Y equals 0, all of them are 0. Y1, we have 3, we have 5 1s, we use 3 of them. If we want to reach Y equals 2, 2 1s, and 2 2. For Y3 here and for Y4 here. For Y5, we can't reach that, because if you add all these things, 5 1s would be 5, 2 plus 2, 4 plus 4, 13. If Y is greater than or equal 5, then if you have 3Y greater than or equal 15. But 3Y we know is less than or equal 13, because all the biscuits, some of them is 13, so that's a contradiction. So for Y greater than or equal 5, we can't do that until Y from 0 to 4 is possible. 1, 2, 3, 4, 5. So the answer is 5. Now let's consider example number 2. You have 2 bags and 3 types of biscuits in the pantry. 2, 1, 2. So let's see here. 2 1s, 1 2, 1 4. So if we want to check, we can say, okay, we have 2 bags. So for 0, that's okay. For 1, you use 2 ones. For 2, you place 2 here and 2 ones here, so 2 is okay. For 3, you can't do that because 2, 1, 3, and the other 3 is impossible. For 4, you place 4 here and 2 ones here, so 4 is also possible. For 5, you have 2 4s. So for 5, 4, 1, 4, 1, it is possible. For 6, 4, 2, and the next one, 4, 1, 1, 6 is possible. And if you add up all of them, 8 plus 2, 10, 12. So at most you can have 6 in each of them. So let's count 1, 2, 3, 4, 5, 6. The answer is 6. Now, it has some constraints. K is between 1 and 60. Q, the number of scenarios, is at most 1000. X, the number of bags, is at most 10 to the power of 18. AI is at most, this means the number of biscuits from type I. And for each call to count tastiness, the sum of tastiness values of all biscuits means what? A0 times 2 to the 0. How many biscuits of type 1, A1? Each of them, tastiness of each of them is 2 to the 1, 2A sub k minus 1, the last type, 2 to the k minus 1, is at most 10 to the 18. And this condition is important because in the last of this problem, we should count and find the number of operation and order of that. So we would use that. It has 1, 2, 3, 4, 5 subtasks. We solve this problem without any constraints. So our solution would be okay for all these parts. On sample grader, you have at first of the input Q, the number of scenarios, and then you have Kx, the number of types of biscuits, X, the number of bags, and then A0, how many biscuits of type 0 is 1, and K minus 1. The output you should print in line I, return value of count tastiness for the ith scenario in the input. That was the problem. So for these problems, considering a small example as also IMO is really important. You, for example, try to consider a small example of K when you have one type of biscuits. So suppose that you have A0 from type 1, all of tastiness of all of them is 1. So if I want to place in each of them Y, so YX must be less than or equal A0, because the sum of them would be YX, and you can reach in all cases if YX is less than or equal A0 because all of them are 1. So you only consider Y1s, again Y1s, and here Y1s. So yx must be less than or equal sum of them, a0. So y is greater than equal 0, less than or equal a0 over x. Since y is an integer, you can say it's less than or equal floor or integer part or GIF of a0 over x. So the answer is GIF of a0 over x plus 1. So we found the answer in the case k equals 1. Now let's consider when k equals 2. In this case, you have A01s, A12s. Now, case 1, if you want to make y, that y is even. So if y is even, if we want to use 1, we should use, in for example, 1 bag, we should use even number of that. So you can consider each 2 ones as a 2. So you have A0 over 2, 2's more, and A1 2's here, A0 over 2, the GIF of that may be 1, 1, or 0, 1 remains. Now, all of them are 2's. It is like the KP previous case that all of them were 1's. So the answer is number of 2's over x GIF of that plus 1, exactly like this. Floor of a0 over 2 plus a1 over all over x plus 1. Now, in case 2, if y is 1, so we place in each bag 1, 1, and then for other ones, because in each, all of them are 1, so you have odd number of 1s, so you consider 1, 1 for each bag, and then change all 1s, all 2 1s to 1, 2. So we have a0 minus x1s. In this case, a0 must be greater than equal x. Otherwise, because if a0 is less than x, so you can't place at least 1, 1 in each bag to reach the y that is odd. So for the case that a0 is greater than equal x, you use 1, 1 for each bag and then change this to 2's, and like previous case, you have a1 plus a0 minus x over 2 floor of this, and similarly you would reach this number of cases. Now for K2, if you want to simplify the answer for a0 less than x, in this case only y is when y is even, and for a0 greater than equal x, you would reach this. Now we understand something by considering these small examples. For example, if we consider 5 1s, 2 2s, and 4 and 3 bags, let's check. Y0 is possible, Y1 is possible, Y2 is possible like this, Y3 is possible, and Y4 is possible. Now, is Y5 possible? If you check some of all the tastiness of the biscuits, would be 5 1s, 5 plus 2 2s, 4 plus 1, 4, 5 plus 4, 9 plus 4, 13. And this is less than 3y. So one of the necessary condition is what? If you add up the tastiness of biscuits from A0 to AI, and you want to reach y for each bag. Suppose that y is less than or less than 2 to the I plus 1 greater than equal to the I. So we can only use 2 to the 0 to 2 to the I, because if you use 2 to the I plus 1 for one bag, then it would exceed it than y. So it would exceed than y. Now we consider only type 0 to I, so the sum of them must be greater than equal xy. So for y between greater than equal 2 to the I less than 2 to the I plus 1, bi as defined like this must be greater than equal xy. So we've considered first condition by considering a small example. Now suppose that, for example, we want to reach y equals 4. We say 1 4 2 2s 4 1s. So we can change, for example, if you have 2 2 to the j, we replace it to 2 to the j plus 1. So by using this, we would reach 1 1 would be 2, 1 1 would be 2, 2 2s would be 4 4 4. For example, for y equals 0 3, we would use 2 1 2 1 and 3 1s. And if we use that again, we have 2 1 2 1, and these 2 1s like this would be 2 1. Now we understand something. If y is greater than equal to the I and less than equal to, and less than 2 to the I plus 1, if we write y in base 2, 2 to the I plus I1, 2 to the I1, and 2 to the IS without loss of generality, because we know that I is the greatest one, you can consider they are in strictly descending order. Now, all of them are different. If we use this action, then for each of them we would reach 2 to the I, and for each bag we should reach the rest of that, means y minus 2 to the I. So by this thing we would reach necessary condition 2 for y greater than equal 2 to the I less than 2 to the I plus 1, and when I by is good, y minus 2i must be also good. Like here, for example, 3, when 3 is good, if you subtract 2, 1 must be also good. You can reach 1 here. Now, we've reached 2 necessary conditions. Now we want to prove something. If necessary conditions 1 and 2 are satisfied, then we can say y is also good. So let's consider, suppose that y is greater than equal 2 to the I and less than 2 to the I plus 1, and bi this is greater than equal xy, and y minus 2i is good. We want to prove that y is also good. So we know y, but this necessary condition that y minus 2i is good. We can reach y minus 2i for each bags. Now, if we consider for each of them this, then if we do this action again. If we have 2 to the j, then we change it to 2 to the j plus 1. So we can say for the j strictly less than I. So the number of ones after reaching y minus 2i, because we know it is good, then if we do this action until we can't do that, then the number of ones is at most 1, number of twos at most 1, number of 2 to the I minus 1 at most 1. And now if the number of 2i's is at least x, then we place 2 to the I for each bag and we would prove the problem. So if we want to prove by contradiction, assume on contrary that the number of 2i is less than or equal x minus 1, let's add up all the tastiness. So bi is a0 times 2 to the 0 plus ai 2 to the I is at most y minus 2i times x, because we placed these tastiness on the bags, plus we know we have at most 1 1, at most 1 2, at most 1 2 to the I minus 1, we add all of them, plus 2 to the I times x minus 1. Assume on contrary here. So y minus 2i times x plus 1 plus 2 to the I minus 1 would be 2 to the I minus 1, like this, plus 2i x minus 1. If we expand all the terms, we would reach yx minus 2 to the ix plus 2 to the I minus 1 plus 2 to the ix minus 2 to the I. Minus 2 to the I and 2 to the I would be cancelled. Minus 2ix plus 2ix would be cancelled, and it would be yx minus 1. Now, we proved that bi, by assumption of the contrary, that bi is less than or equal yx minus 1. But from the main assumption, we know that bi must be greater than equal xy here. So xy is less than or equal xy minus 1, and that's the contradiction. So we've proved that y is good. So if we write it again, y is greater than equal 2 to the I less than 2 to the I plus 1, well, then y is good if and only if bi is greater than equal xy, and y minus 2i is good if and only if between these two things. Now, we want to count by this, we can call it lemma. By this lemma, we want to find the number of y's that are good. So suppose that from 0 to 2 to the I minus 1, m1, m2, and ms are good. Now, like this, we know if here something is good, minus 2i of that is also good. So minus 2i of that must be m1 or m2 or 2ms. So we only, for the goodness of the y's here, we only need to check m1 plus 2i and ms plus 2i. We know they are good, but we need to only check which, for example, ml, if you place it, won't satisfy this condition, that some of the bags would be, in that case, greater than bi. So we should check this condition. We would say ml plus 2 to the I times x, because we want to place in each bag ml plus 2 to the I, bag number x, ml plus 2 to the I. So ml plus 2 to the I must be less times x, because we have x bags, must be less than or equal bi, this condition. You can call this one y. xy is less than or equal bi. So ml plus 2i is less than or equal bi over x. Since it is integer, it is less than or equal floor of bi over x. Now ml is less than or equal bi over x, floor of that minus 2 to the I, and we know ml can be greater than equal 0. So we have also this condition. Now let's consider Cn, the number of good numbers, good y's, we can say good y's in 0, 1 to n minus 1. So if n is less than or equal 0, Cn would be 0, C1 would be 1, because from 0 to 0. You consider for each back 0, so one good case is possible. Now for n greater than 2, greater than equal to, suppose that n is between 2 to the I less than or equal to 2 to the I plus 1. So we should consider, we want to find a recursive sequence for Cn. So we should consider 0 to n minus 1 here. Now we divide to two parts, 0 to 2 to the I minus 1 and 2 to the I to n minus 1. We want to count until here. Now, we know from 0 to, for example, 2 to the I minus 1, we have y1 to yt that are good. We call them C2 to the I by this definition of this recursive sequence. Now, we know y1 plus, by the previous page, we know y1 plus 2i2, yt plus 2i. All of them are good, but we should check the sum of them must be less than or equal bi, and also we should consider on until n minus 1. So since we should consider on until n minus 1, so yl, for example, if until yl is good, yl plus 2 to the I must be less than or equal n minus 1, and also yl plus 2 to the I times x, because each bag is yl plus 2 to the I, we have x bags, so some of them must be less than or equal bi. This is xy. So if we write it, all the things here again, and try to simplify, yl plus 2 to the I less than or equal bi over x floor of that. So yl is less than or equal bi over x floor of that minus 2 to the I. And here yl plus 2 to the I less than or equal n minus 1. So we can conclude that yl is less than or equal n minus 2 to the I minus 1. Since we want to use C, for example, CTCS, we should, for Cn, it was between 0 and n minus 1. So since we want to use for C, for example, related to this, we can say it is less than or equal n minus 2 I minus 1 plus 1, which is this, and for this one we add plus 1 to them. Now, if we want to use that, we can say C2 to the I. We know that YL must be less than this, YL must be less than this. So YL must be less than minimum of n minus 2I and GIF of bi over x minus 2I plus 1. And we can write minimum of n and GIF of bi over x plus 1 minus 2I. Because minus 2I was common for these two terms, we can write it. So we know that YL is between 0 and strictly less than this. By definition of C, recursive sequence C, we can say it would be C of this. So we would write C of minimum of this minus 2I. For n1, we said C1 is 1. For n less than or equal 0, Cn is 0. Now, we should consider the time of this problem and n greater than equal to, and between strictly greater than 2I less than or equal to I plus 1. We want to find the time of this problem order of that. We can say we should find C1, C2, C2 to the 2 to C2 to the I, and until the last n that we want to find. We know n is less than bk minus 1 because bk minus 1 is sum of all tastiness, and we can say strict great less than or equal this. And the problem says, in the assumption of the problem says it is at most 10 to the 18. So now that we want to find C1 to C2 to the I2 to the I is less than or equal 10 to the 18. So I is less than logarithm of 10 to the 18 is order of k, we can say. And now when we want to find 2 to the I, by this theorem, we say 2 to the I is sum of 2 to the something less than that, and 2 to the I minus 1 plus something else. So again, you for this one, you use 2 to the I minus 2 and other things. So you can start from 2 to the 0 means C1, find it, and then find the next one. And for each of them, you should do this for order of k. And since there are k, it would be order of k squared. Now for n, we know n is at most 10 to the 18. Like this, you at first you found C1 to C2 to the I that you need them. For n, you use this, and 2 to the j plus c of this plus c of something. Again, you do this, and each step you can say it is around n would change to something around n over 2. So for finding n, it would be order of logarithm of n, and it is order of logarithm of bk minus 1, order of logarithm of 10 to the 18, which you can say is order of k. Since at first you found order of k squared, combination of them would reach order of k squared. And at last, since you have k scenarios, it would be O order of k squared times q. K is at most 60 and q is at most 10 to the 3. So order of k squared times q would be good. And that's a good place to finish this problem.